we'll start with the next set of lectures looking at branch and cut now for global mixed integer nonlinear optimization, in particular for problems that are non-convex, not just because they have integer variables, but also because the nonlinear expressions themselves are non-convex. So there's some added complexity, and we'll take, so over the next 3 lectures, I'll take you through how to amend the algorithms that we had seen earlier. So the plan is to look a little bit, first of all, just to familiarize ourselves again with global optimization for now non-convex mixed integer nonlinear optimization. We'll look at how we can construct relaxations for specific functional forms. And so I'll just do some small examples here. In the next lecture, I will talk about a general tool for doing this. And then I'll give a short introduction to spatial branch and bound. So this is the technique that we use to refine the relaxation of specific nonlinear functions. And this first lecture is more of a, sort of gives you the framework or the outline. The next lecture is going to give you more details, and hopefully that helps us get to grips with it. Okay, so here's a short definition. You've seen this before. We're now looking at a non-convex optimization problem. And in particular, the problems have been non-convex before because we had binary or integer variables. But in this case, I'm also assuming that maybe the functions g that define the feasible set f or the objective function f themselves are non-convex. And the definitions that I've given here are the same definitions that you've seen earlier. We call a point a local minimum if within a neighborhood of that point there are no better solutions. So in other words, I can construct some neighborhood of my point, and there are if I take a point inside this neighborhood, intersect it with the feasible set, then the function value of this point that I took out of this neighborhood is greater than or equal to the function value of the original point. And a point is called a global minimum if I can just take this neighborhood to be infinite. So there is no better point than this point that I've chosen earlier. And it's not clear maybe how to do neighborhoods in mixed integer nonlinear optimization, and that's quite all right. So for integer variables, a neighborhood is maybe not well defined, but you could imagine, for example, taking the neighboring points or on some lattice, then the points that are within a certain distance of the current point. So here's a quick illustration what I mean by local minima. The blue points are local minimizers. So if I take a small neighborhood, if I just look at a small neighborhood of this point, then all the points within this neighborhood are larger than this point, similar for this point. And this green point here is a global minimum. So I can look at any point on the whole x-axis here, and the function value is always greater than or equal than the function value that I had there. And so when we have non-convexities, then we have seen that the feasible sets can be quite disjoint. We have seen this for the power grid example, where the feasible set was this very involved nonlinear curve, or it could even be disjoint. And there could be, on top of that, there could now be many local minimizers. So in particular now, if we start a method, a gradient method, then it might get trapped in a local minimum here. Okay, so we have to somehow do something about this. And we're using the same trick that we've been using throughout the course. So the good news is you don't have to learn anything new. You just have to find a convex relaxation. Okay, now somebody should say, how the hell do I find a convex relaxation of a nonlinear function? And that will be part of what I'll teach you over the next hour. So we know how to relax integrality. That's easy. We'll just pretend that the variables are real instead of integers. So if I have a number of integer variables, my relaxation is the same as before. I pretend that they're now real variables. That convexifies that part of the feasible set. But somehow, if I have this nonlinear objective function, I also have to find somehow there's a convex relaxation. So somebody has to magically give me this green function that underestimates my nonlinear objective function everywhere. And that's the hard part. And there's 2 things we want to do. Is one, we want to ensure that it is a relaxation, so it lies below the original function. And two, we need to make sure that we can solve this problem. It's tractable. So for that, we need something like convexity, so that we can have algorithms that guarantee to find the global minimum. And then the next step that we're going to do is then constraint enforcement. So we had these two parts in the branch and bound algorithm. One is constraint relaxation. So that's good. I get a lower bound when I find this point down here. But I'm not interested in this lower bound. I'm interested in this global solution here. And this lower bound can be very far away from this global solution. So I need to have some way of branching. And so by branching, I mean that I somehow find a way of refining my this nonlinear relaxation that I have here to get a tighter relaxation that now corresponds to maybe two nodes in my branch and bound tree. So I have a left node here and a right node here. But they're constructed not just by branching on a variable, but also by then modifying this underestimator separately in each of these subtrees. So we'll go through this a little bit in more detail. So the first thing I want to tell you about is how to relax specific functional forms. And so I have some simple examples here and one exercise. So let's do this really quick. So you already know a way of relaxing functions that you can apply here. And so the next slide should look familiar to you. So I can look at this function, xk is equal to xi squared. And the feasible set is this solid black line that you see on the left-hand side here. The solid black line is the set of points where xk is equal to xi squared. And so we know that xi squared is convex going up, but the equation itself is not convex. And so the feasible set that lies between, if xi is between li and ui, then the feasible set is the secant, the set enclosed by the secant and by this nonlinear function here, this nonlinear function here. So my feasible set is all of this here. It's not very clear. This is the whole, all of this is the feasible set there. Okay, so a relaxation, we can do this. We can do use our old friend, the supporting hyperplanes to nonlinear functions. So Pietro, I think, created this picture. So there's 1, 2, 3, 4 supporting hyperplanes here, or 5 if you can also take this line there. And that would give you a feasible set that is slightly larger, or it's a lot larger actually, but it underestimates your convex function on this side, and you have the secant on the top. So you now have a polyhedral relaxation. So that's nice. We have a relaxation that's made up of linear, of affine constraints. And I can do that whenever I know that I have a function that's convex that takes part in this nonlinear equation here. So if I have a convex function, I can get my underestimators, and then my feasible set is bounded by these underestimating functions and by the secant. So that's the polyhedral set there. Okay, now you can do slightly better if your variables are actually integers. So if xi is an integer variable, then it can only take points that are sort of discrete values. And then I can actually use secants rather than my supporting hyperplane. So now I do a secant from xi equals 1 to 0, another one from 0 to -1, and then from -1 to -2, for example. And now the feasible set that I get is this area here that's enclosed by these 4 lines that I have there. And so that's much tighter. Now, quick question, what happens if xk is an integer too? So now I have an integer that's along the x-axis. If I have an integer that's on the y-axis, what can I do? Can I improve this further? You don't think so? Who thinks I can improve this further? I'm making this up. I think you can. So if you know that you have integers on the x-axis too, then the feasible set are the integer polyhedral. And so you could potentially look at finding the convex hull of those, but that might be harder. You can do this for all sorts of functions. So you can do this, for example, for xk equals xi cubed. Now you're exploiting the fact, for example, that the function, you can compute, again, you compute secant or supporting hyperplanes, and as long as you know where the function is convex and where it is concave, you can construct these polyhedral outer approximations. So for very simple functions, if you know the function well enough, you can construct polyhedral outer approximation or relaxations. So that's good. That's something that's relatively easy to do. And I'll show you next how to get these guys here. So that's a very special one. This bilinear term that pops up in many special problems, this bilinear term, and you can sort of, the nonlinear function is illustrated by this this function here, this colorful function, and the polyhedral set is bounded by these facets of, you can actually show that that is the convex hull of this set. Okay, so for simple functions we can do this, but are there more general, more interesting functions for which this works as well? And so here's one particular function. Ignore the odd degree monomials, but for bilinear functions, we can actually construct these underestimators, and they're called the McCormick underestimators. So they have a name, they're famous, and so you can show that the convex hull, this set theta k here, the convex hull of this bilinear term is given by these four sets of equations here. So they look daunting if you haven't seen them before, but they're really, really easy to derive. And so here's a little exercise. And I was going to split you up into 4 groups. So we can split you up down the middle, and then in each middle, half up, half down. And you guys are going to do the first behind. So you do this one on the left here. Next group behind you does the one on the right. You guys at the front do the one on the left bottom, and the group behind you does the one on the right bottom. So get together in your groups and see if you can construct one of these valid underestimators. And I'll give you sort of a couple of minutes to at least chat, talk, draw something on a line. Hint, you want to use these bounds. So you want to use bounds such as these to construct these underestimators. And then we'll get one of the groups to tell us how to do it. Okay. Okay, does any of the group have, oh, we have one group ready. You probably are ready too. How about the other 2 groups? Are you ready? Which of the bounds should we do? How about we do, which one did you do? Sorry? Oh, the left, UJ, UI. Okay, UJ. So I'm naming the bounds by their last, what's written at the end. So, and that's a hint. So what did you do? Okay, so you took the 2 valid bounds, which is ui minus xi, and you multiplied it by ui uj minus xj. Yep, and we know that because these are valid bounds, these are both greater or equal to 0. So when I multiply them together, I have something that's greater or equal to 0. Okay, and then you just multiplied them out. Okay, so you then get ui uj minus xi uj minus xj ui plus xi xj is greater or equal to 0. And then what did you do next? You realized that this is xk, and then you rearrange everything. Okay, so that's then equivalent to xk greater or equal to, and now I want to write it the right way, so I write ui xj plus uj xi minus ui uj. Okay, that's one. And you now rinse, wash, and repeat. So next one, so this is we called it the uij bound because those were the two inequalities that we multiplied together. So we can do another one. You can do xi minus li times uj minus xj. That's again greater or equal to 0 because each of the individual terms that you multiply are greater or equal to 0. Okay, and then you multiply this out, or expand, which is the better term probably. And then you assign or replace the xi, xj term by xk and rearrange. That's it. And so now you know how to do McCormick underestimators. It's really nice and easy to do. Can you do this for more than 2 variables? Who thinks we can do this for 3 variables? Okay, yeah, we can do it for 3 variables. Do it for 5 variables, right? You just use the fact that you know these bounds. That's all. Okay, so that's a nice, cool way of getting convex underestimators for a very generic function. One caveat that's written here is that the tightness of this convex hull depends on the tightness of the lower and the upper bounds. And you kind of see this because on the left-hand side here, you're subtracting potentially large numbers. If ui, uj are very large numbers, then this makes it a very low lower bound. And so if they have the same sign, then this would be a very large lower bound. And we'll come back to how to make these tighter. Okay, so now we can use this and other techniques to construct a convex outer approximation or convex underestimator of our non-convex function. And so we're now ready to sort of think about branch and bound screening. So this is again going to be an implicit enumeration scheme similar to the integer branch and bound that I showed you last week, where we recursively refine the partitions. So in this case here, if we look at these underestimators, we can refine partitions by changing the bounds, li and ui. So we can branch and thereby changing the bounds, making these potentially tighter. And we would just use these reformulations and other reformulations that I tell you about in the next half hour to construct these outer approximations or underestimators. And most of the time we will be solving linear optimization problems. So we will construct linear optimization problems. These underestimators here are linear underestimators. They're linear functions in xi and xj. So they're affine polyhedral constraints. And there's 2 pieces of code. This goes back, or some of this goes back to some papers by Smith and Pantelidis, but it was also Nick Zahanidis and Moed Tavallamalami who popularized this and wrote the first solver to do this rigorously. And then Pietro has a very nice solver that's published in open source format. Okay, so then once we construct these polyhedral outer approximations or our relaxations, so here's the relaxation again on the left-hand side of xk equals xi squared. And you could imagine that if you're solving an optimization problem over this region, so now the feasible set is this region here that's inside this slightly gray area. And if I minimize over the feasible set, I might find that my solution xi hat, yj hat, lies somewhere in this region, but not on the feasible set, which is just the black line here. So we are somewhere inside the feasible set. And in that case, we need to somehow eliminate this constraint, separate this constraint from the feasible set. So the feasible set is this non-convex black line, and one way of separating this constraint is to find a branching point, B, and it could, for example, be the function value of xi here that I took here. I didn't take it here. And then get two new problems, one on the right-hand side, where we replace the nonlinear function in this area between B and ui by, again, a polyhedral outer approximation. And the other one is on the left-hand side, and again, we get a polyhedral outer approximation on this left-hand side between Li and B. So we now have done the same thing that we do in integer optimization when we branch on a variable. Here we're branching on this non-convex expression, and we refine, by branching, we refine the outer approximation that we have. So this is a general procedure. So we now have one set over here on the right and one set here over the left. And we have this disjunction where we say either my xi is less than or equal to b or is greater than or equal to b. And we've excluded the point up there because we've refined our outer approximation in these two areas. So there's two parts now to the branching. One, we need to find a branching point, and then it's less than or equal to b or greater or equal to b. So that's different to the integer optimization because the branching point is kind of not excluded. But we also need to refine the outer approximations that we have on both these areas. Okay, and so you could find branching points, and here's one way of just picking a branching point. So I have this exponential function here. I want to be xk is constrained to be e to the xi. That's this function here. The feasible set between my lower and the upper bound is this nonlinear curve, the black nonlinear curve. The one relaxation is taking the secant, because I know that the exponential is convex, and then two supporting hyperplanes at these points here, and then I get the light gray area as the outer approximation of the set. And so I can now think about choosing where do I want to choose this branching variable, and one strategy might be to choose it in such a way that I maximize the area of my relaxation that I can throw away. So here, this looks like it's quite a nice little area, but over there it's maybe too large. So maybe I want to change the B. But that's a hard problem. So typically we're not going to do this. But you can, maybe for some problems, for some specific functions, you can actually work out where those ideal branching points are and then branch in such a way, potentially. And there are a number of things that we carry over from the integer optimization branch and bound. So all the good ideas that we had there, the strong branching, where we're deciding we have a whole set of variables that we can potentially branch on. So there might be a whole set of these nonlinear functions that we can branch on. And we would like to explore all of them and then use the one that has the biggest impact on the lower bounds that we get afterwards in the branch and bound tree. So all of these ideas generalize from the mixed integer nonlinear optimization case. And they're still important to use. This branching on nonlinear expressions is also sometimes called violation transfer, because we are at a point that violates our nonlinear expression, and we change this violation and we split it out between two problems. So over here, we sort of this violation at this point was really quite large, and we sort of transferred it into two new problems. So one of the issues that we need to make sure is that we need to exclude the previous feasible point in these new linearizations that we're generating. And the reason for that is that our branching no longer excludes, for example, the point xi. So notice that when I branch at this branching point b, then I say either xi is less than or equal to b or xi greater or equal to b. But that means that xi is still feasible in both these subproblems. And that was not the case in the integer case. In the integer case, we branched below the floor and above the ceiling. So there was always a gap. Here, there's no longer a gap. The reason we get away without that is because we have this refinement property of the approximations that we're doing. So while we're branch and we refine the approximations at the same time. So that's very important to do. Okay, so here are the main takeaways. Global optimization of non-convex mixed integer nonlinear problem is really much, much harder. And you saw that in the complexity results, we can maybe solve problems of hundreds of variables. If they're mixed integer nonlinear optimization problems, this is much, much harder to do. Because in addition to branching on the integers, you now also have to branch on these nonlinear expressions. And that requires, one, that you find good underestimators for these nonlinear expressions. And I'll give you a way of doing that in the next lecture. And two, you need to be able to refine and tighten these underestimators efficiently. And that's much harder than in the integer case. And the reason it's much harder is because there's so many more nonlinear functions around than there are sort of integers, right? I mean, there's an infinite number of nonlinear functions. And so branch and bound then can take advantage of this in a little bit, that you can branch both on integers and on these continuous nonlinear expressions at the same time. And you can sometimes exploit that to construct tighter relaxations by using the fact that some of the variables are constrained to be integers. So that's the second part here, where if you know that your variable that's between Li and Ui is an integer, then you can restrict yourself to the integer points and get away with secants, for example. Okay, so that's a short introduction to mixed integer nonlinear optimization over non-convex functions. And so if you have questions, please ask them now. Or forever hold your peace, as they say in church. Don't worry, we're not going to marry anybody away. We're kind of marrying integer optimization and non-convex optimization here. So maybe that's appropriate to say then in that case. Yep. Okay, so explain the branching again. Okay. So how do I choose? I haven't told you how I choose the branching point. One way of choosing it is to take as the branching point the value of the variable that you had at the relaxation. So when you solve the relaxation, which is this light gray area here that's not showing up very well on the screen, unfortunately, that's why I'm outlining it here. So this light gray area here, you could choose B as the solution at the relaxation. That's one way of choosing it. And that's probably a good way of doing it, because then this B will go together with the value of xi. It'll go together with the value of xj. And you can now refine this relaxation to make sure you separate. You no longer, this xj is no longer feasible. So that's very important to make sure. I kind of got ahead of myself and said, well, you can also ideally choose it to maximize the area that is removed. But one problem with that is that your relaxation point might now still be feasible in the problems that you generate. So that's maybe not a smart way to do it. Correct, because, well, so unless the relaxation point was actually on the function. So if the solution of the relaxation was on the function, then it would be feasible, but then we wouldn't branch, because then we're feasible. So otherwise, this relaxation point has to lie somewhere on the line that's going up and down here. And so then, because I'm now enforcing my secants exactly at these points, I will exclude that point. Thank you.